they have medium problem given the square matrix or grid with binary numbers 0 or 1. We want to swap the rows so that the upper diagonal is all zeros. And this single swap is +1 to the result, and we want to find the minimum number of swaps. So the solution is, the first you have to walk every row one by one and count how many zeros at the suffix we have. So this is 0 zeros, this is 2 zeros, sorry, 2 zeros, and this is also 2 zeros. Now the problem became like one-dimensional. 0, 2, 2. This is a single array of numbers, and we want them to be not less than some target, and this target is we have exactly n-1 zeros at top, n-2, and this is n-1, so it's allowed to be at least 0 zeros, and so we have to be bigger than that every time, and this is our target. Now the problem is, how can we rearrange this optimally? Because we know the target is 0, 1, 2, so 2 zeros at top, 0, 0, 1, 0 next, and 0 zeros. Oh, I'm sorry, at least 0 zeros. So at least 2 at top, at least 1 next, and this is at least 0, so not count. How can we arrange or rearrange optimally? What kind of steps or what kind of logic we should apply to rearrange this and make this minimum number of swaps? And the additional intuition is that we only allow to swap adjacent cells, adjacent rows. So that means if we have to move some number up or down, we have to move all intermediate values. So this is a bubble, like in a bubble sort. Not exactly a bubble sort, but like in a bubble sort. Why not exactly? Because we have this condition. This is not precise order, so we can have them unordered but we have to restrict them to have at least this number of zeros, at least some value, at least some target. And to allow this, we can walk from the top position down and search for the most demanding cell. It looks for n-1, at least n-1 zeros. So this is where we can fail fast. So we go and we search all the next items. Is it at least this number, this target? And if it is, we have to bubble it up. So we have to shift the entire middle ground and move this up. And the number of swaps would be the target position that we found minus the current position. Now let's look at the code. I wrote the simple version, not minimized, not optimized, it just counts how many zeros we have at suffix. Then if we compare these values with the target, we searching for the J. And if we don't find, we immediately return -1 because we fail fast, and the answer is the count of J minus I. And then we have to do the actual bubbling up, because this is required, because some we go only in one direction, and we have to analyze what the next what would be the condition of the array after we bubble this up. So this has to be happen. Now let's golf this solution. I've already golfed it of time. I spent 26 minutes by the first variant for this code, and I golfed this solution pretty extensively. So I spent 1 hour. Now let's look at the steps I made. So the first step maybe if I just golf it from the editor, it would be a nice view. So this bubbling up, let's solve it with Kotlin's mutable list. And if we have a mutable list, we can instead of doing this bubble, we can do this like this. Add as at position I, we add in the position that we have removed. So we've taken this, remove at J. This is how it. Now let's check the solution. It kind of works. Now the next step is this one. So or maybe this one. We don't have to check if it's it returns 0. We just can take it like this. Let's check if it works. It should work. The next iteration is that this while loop is unnecessary. We have a Kotlin for this, and just let's find it with Kotlin. So ij size. Let's just find the solution as it less than size minus a minus 1, and also this return on null. So j minus I. This is much shorter, but this is not the finish line. Okay, I was wrong. So what was wrong? While we want to find the bigger. So okay, this should work. It works. Now, when we're doing this kind of plus at position I. We never actually whenever would go to this position, so we can just remove it, not add it back. So let's just remove it. So we are removing it, not adding back, but that means we have to start always with 0, and we have to remove this I at the end. And this S0 from S size is just S, well, I will show it like this, S indices. It is shorter than this range, a little bit shorter. Now let's look if it works. No, it not work. Why? Why? Because we have maybe this, maybe this one. I'm not sure why it not works. It should have worked. Maybe this S size is not correct. Okay, this is not working. Let's return it back. We are going too fast. Let's optimize this one. So instead of looking for the suffix count of zeros, let's find it last index of 1. So this is pretty much the same, but this is reversed. Instead of suffix, we find size minus suffix, and when we have size minus suffix, we can make it just size I. If it works, it doesn't work again. Why not? Why not? I don't understand. It works on my okay, I just check it for myself. Quick check. This is a final solution that I have, and why it doesn't work? Okay, this should work. And this is S indexes, and this is without removal, and this is just J, and this should work. Why not? Yes, it works. And the final micro optimization is that this line is too long. We can make it like this, array list. Oh. What's this? Array list. And then run. And then equal. We don't have S anymore. Let's check. Yes, it works. Now we can collapse some very short lines in a single line. So that's how it works. Now it looks at the Rust solution. It's almost the same logic. The Rust is a little bit verbose in his expressions. So we have to iter, it's taking ownership, and then air position. And this try fault is very nice because it takes this as position. And if we have any value as known, we will return early to this unwrap hole. So that's it for today.